And now, Ari, are you online?
Hi, are you able to hear me?
I can hear you. Can
Perfect.
you share your? Yes, and we can see your screen, so feel free to start.
Perfect. Thank you so much. So yeah, thanks so much for the organizers. I've actually been traveling a lot this week, and I'm really grateful for last minute adjustments that I requested, and they kindly were able to put together. So thank you very, very much. So essentially, I'm interested in making sure that we are doing gravitational wave counterpart discovery more efficiently and basically filling in a lot of the bottlenecks. With more appropriate machine learning solutions as and when necessary. I'm currently a faculty member at Drexel. So essentially, since this is a short talk, I'll jump right into the situation that whenever we receive a gravitational wave trigger, along with some information that we get promptly, for example, a sky localization, some machine learning based inference on the gravitational wave strain that tells us something about the merger and what it contains, and something about the signal. We are tasked with sort of thinking about a whole bunch of transients that surveys are detecting that would be consistent with the localization region, and trying to figure out whether which one of these would be the true event. And in addition, we are usually worried about thinking about a limited number of resources that we have on hand, either photometry, spectroscopy, or any of those, to allocate to figure out which the true candidate might be. And sorry. And essentially, this sort of a problem is challenging because in order to make these allocations, you have to sort of like keep in mind that you're at the moment that you're making the decision, you're seeing incomplete information. So if you have made a decision to spend something really expensive, like getting a spectrum on one of the transients, and it turns out to be not a good choice, you lose something. So there's this whole issue of like how to make sure that we are allocating the budget correctly. And usually people want to solve this with classifiers. So let's imagine that, our list of transients are broken down this way, and we have a very powerful classifier that can assign some probabilities. The issue here is that if we want to then do this matching of like saying, hey, we have a limited number of budget, let's try to figure out which one the true kilonova is. You don't really get to know off the bat how to actually make this mapping. And one of the more naive things you could do is probably allocate to your most confidently classified event at any given time, and then sort of like fill in the bucket as you go downstream. But as I mentioned, this can be challenging because it could be possible that in hindsight, this was actually not the right one. So when you make budgetary decisions on how to make allocations, you may eventually, for example, do better ruling out some candidates earlier versus spending it on something that you believe would be the best one. So essentially, follow-up decisions are hard because you can misallocate them. And in many cases, this is only apparent with a delay. So you don't really see whether or not you made a good decision right now. Uh, and this is extremely hard to do, especially when you want to constrain physics from the light curves. So essentially, really the true solution here is using reinforcement learning. And the way sort of like I would like to explain it would be to say that this is a discretized version of the world that we are talking about, where we encounter like a state of the world. Imagine these as a bunch of light curves that, given a bunch of things that we can do, can devolve into a bunch of other states, and so on and so forth at every given intersection. And this tree goes down. And the idea is to be able to find the optimal path right up front, and you do not want to be misguided at a given step. So even though, for example, it looks like locally this was the most optimal thing to do, the true optimal solution would have been this way. And to really solve it, you need reinforcement learning, which essentially figures out what the best downstream benefit might be, even though you see incomplete information. So essentially, we just use this formalism to solve a very reduced problem where we had nine transients. One of them was the kilonova, and the other were all various contaminants. And the objective of the reinforcement learning agent was to figure out how to spend a very limited budget, which was just one additional photometry, such that you maximized allocation to the true event. So this was sort of like a target hitting practice for the agent, and you do well if you do it regularly and well. And essentially what we found was that we were able, for a very, very simple model that we started off with, which is linear value function approximation, which is linear regression in reinforcement learning. There are benefits to using this, and I can talk about it offline, and in the submitted version of the paper, it's been discussed. What we found is that we actually did better than random, which demonstrated that the problem is learnable. And then in addition, we actually did comparison studies to experts who actually do, this type of decision making in real time in search for gravitational wave events. And we weren't able to beat them given the simplicity of the model. But there's optimism to think that if we just switch to neural networks and representing the Q function, you'll do really well. And essentially, here's just the summary of all of that. Pythia is the name of the agent, and was very easily beaten by the human expert. These types of comparison studies are necessary, by the way, because in reinforcement learning we don't have access to the ground truth. So essentially, benchmark studies like these are pretty much key to showing that you're actually doing a good job. We did a bunch of tests to figure out, sort of what the agent was learning, and we did comparison studies of like the human expert. A very key fun fact was that in situations where the true kilonova was not as evident, so these would be kind of like a bluish type of kilonova. When human experts were faced with like a conundrum of like, is this really the event? They would spend their budget to try to rule out a bunch of things. On the other hand, the artificial agent would just like give up and spend all his budget randomly. And the reason was because we did not incentivize exploration when it's not doing very well. So essentially, given zero rewards at any given time, it doesn't really matter. So it just settles into whatever local equilibrium it found. Reinforcement learning is very expensive computationally, and there's a lot of carbon footprint that you get from training something like this. So we spent about 1,210 kilograms of carbon equivalent in training our reinforcement learning models, which is approximately equivalent to a one round trip flight from LAX to JFK. There is a really strong incentive to try to use hardware that can make such inference better in the future. So I'll stop right there and take questions.
Great, thanks so much. So first, I will check if we have questions in New York. No? Do we have questions in Paris?
Well, I do have a question, maybe. Specifically on the last slide, actually, I was wondering, so what's driving the budget for such a high cost of carbon?
So basically what happens is that, so in our case, what we did was we were representing the state space using a convolutional neural network. And in order to evaluate the Q function per state action pair, we have to actually do many, many forward passes. So in our case, since there were 9 events and 3 action per event, there were 27 possible state action pair per state action. So we had 27 forward passes to evaluate each time. And each initial condition was, so there were 7 time steps that were evaluate so for every situation, there were 7 time steps that finished one episode. And we trained for 5,000 episodes with a bunch of initial hyperparameters, and each of them consisted of a single forward pass. The issue here was we used a linear value function approximation, which limited us from sort of getting the Q function per action, because it's, you just get one number out of it. So that was actually really driving most of the budgetary limitation, and we couldn't even scale up to a large action space because of that. But if you switch to deep Q networks, you can actually you do this mapping differently, right? You have the state function, and then you map to the Q function for each action in one iteration. In our case, we just did it because it was an exploratory project. We ended up like training something, and it just took a lot of time to do these forward computations with all the episodes, all the initial conditions, a bunch of hyperparameter searches, and it was expensive.
Thanks.
Okay, questions on Slack? If not, let's thank all of our speakers for the session again.